Screen recording. Okay. Alrighty. So this is going to be the quiz 3 review for Physics 131. We're going to be going over problems that involve Newton's laws, and then towards the end of the session, I'm going to go over some important problems and concepts, things to hit on before the quiz, so you guys kind of know what to expect, roughly. This quiz is tomorrow, I believe. Kind of depends maybe on your professor. I know that Dr. DeJong's sections have their quizzes on Wednesdays. I'm not sure about the other professors. But if anything, your quiz, like if it isn't tomorrow, it'll probably be on Thursday or on Friday or something. Like I'm hoping nobody's taken the quiz already, because then that would kind of, I guess, defeat the purpose of the quiz review. But hopefully everyone's roughly on the same page. I don't think, I guess, like anybody's ahead yet or anything like that. So yeah, I'm guessing the quiz is tomorrow for most people. And then if not tomorrow, then like Thursday or Friday or something. I don't think they ever have a quiz like on Mondays or Tuesdays. So yeah. Anyway, we can go ahead and get started now. So we have this first problem here, right? We have pulling a cabinet. So it says consider a woman pulling a 60-kilogram cabinet to the left with a rope. She had been pulling the cabinet over a hardwood floor, and things were going smoothly, but at the moment shown, the cabinet has traveled onto the carpet, and despite the woman pulling directly to the left with a force of 500 newtons, the cabinet is beginning to slow down at a rate of 2 meters per second squared. So there's a lot of information that we have to kind of dissect here from the beginning with this problem. There's things that are explicit and there are things that are implicit within this problem. So first off, right, we can kind of look over here and see, well, they gave us a mass, right? Mass is important. Oops, that's a huge pencil there. Mass is 60 kilograms, right? So whenever you start a problem, don't immediately go and say, okay, all right, what's part A asking for, right? First, just try and slow down and extract the information, because if you have all the information in front of you, you're going to be able to think a lot more clearly for all the parts coming. So we have mass is equal to 60 kilograms, right? That is the mass of the cabinet, right? So mass is 60 kilograms for the cabinet. She'd been pulling the cabinet over a hardwood floor, and things were going smoothly. But at the moment shown, the cabinet has traveled onto the carpet, right? So this is where things kind of get implicit, right? So we're thinking carpet, right? Try and think or imagine yourself pulling something or even pushing something on a carpet surface, right? There's probably going to be what? What kind of issue might you encounter when you're pulling or pushing something that's heavy on a surface like carpet? Friction, right? Exactly. You might experience a lot of friction. So that's where the implicit information kind of comes in key, because once you hit that carpet, this is probably going to indicate friction, right? And it says, despite the woman pulling directly to the left with a force of 500 newtons, the cabinet is beginning to slow down, right, at a rate of 2 meters per second squared. So now we have kind of a pull force, and we can actually just forget calling it a pull force because we have the rope, right? And so whenever you kind of have a rope and we have a force involved, right, we're probably going to call that a tension force, right? So we're going to refer to this as a tension force rather than a pull force. And then let's see here. It also says we have the cabinet slowing down at a rate of 2 meters per second squared. So the whole slowing down, speeding up, kind of going back to the first couple of weeks, right? You're going to be speeding up if both your acceleration and your velocity vectors are in the same direction. You're going to be slowing down if they're in the opposite direction. So she's trying to pull things to the left, right? If we're thinking friction, right, friction usually kind of opposes your intended motion. So if she's pulling to the left, that friction force, just kind of based on our intuition and our real life knowledge, right, then the friction is kind of pointing to the right, basically, to oppose that force to the left, because it says, despite the woman pulling directly to the left, the cabinet is starting to slow down. So if we're trying to pull to the left, friction is probably opposing that force, pushing to the right, and then we're slowing down. So slowing down, right? If we were moving to the left, then that indicates some kind of negative velocity, right? We're traveling a certain distance over a certain time to the left. And so that left direction indicates a negative velocity. And if we're slowing down, like I said, slowing down means that your velocity and acceleration vectors are going to be in different directions. So that would indicate, right, that your acceleration should be what? Yeah. So acceleration 2 meters per second squared positive, right? So that kind of sounds a little weird, right? Because you would think then, okay, if I'm slowing down, then slowing down feels negative, right? But we have to remember the direction. So we can't just kind of like think about this outside of a physics perspective. You have to make sure that you're integrating things correctly and thinking about things correctly with regards to direction, velocity, acceleration, all that, right? So now that we have everything kind of figured out here, part A tells us we need to draw a free body diagram for the cabinet, right? Labeling each vector with an appropriate subscript. So we can draw our Cartesian plane here, right? Our coordinate plane. This is positive y, positive x, right? Let me choose a different color here. So we already have one force that we're sure of that's given to us directly in the problem, right? What force is that? I think someone already said it, tension, right? Yeah. So we have force of tension that's given to us, right? Because she's pulling left with a force of 500 newtons. Oh, well, there goes the free body diagram there. All right, so F tension this way, right? And then what other forces do we have acting on the cabinet? Friction, right? And what direction is friction to be pointing? To the right, excellent. So friction pointing to the right. Now here's where things get a little bit tricky. So based on our understanding of the problem, right, it says it's going to be slowing down at a rate of 2 meters per second squared, right? We already determined then that the acceleration is going to be positive, right? So if I'm trying to move to the left and my acceleration is positive, right, there's an important definition with regards to the whole F net equals ma deal, right? For the net force equals mass times acceleration, your acceleration vector, right, your value for acceleration is going to match the direction or the sign for the net force. So what does that mean? Well, if my acceleration is positive, then my net force should also be positive, right? Because if my acceleration vector is pointing in the positive direction, then my overall net force should be positive, right? That's kind of the little key there with regards to net force. If net force is positive, then acceleration is positive. If net force is negative, your acceleration is negative, right? Because it just means that, okay, well, if I'm slowing down, right, there's a force that's overwhelming that tension force that's slowing me down. And so if that's the net force that is slowing me down, that net force has to match the acceleration. And so if I was moving to the left with a negative velocity, obviously, there's an opposition of acceleration slowing me down at a rate of 2 meters per second squared, and that's going to be in the positive or right direction. So therefore, my F net has to match the sign of my acceleration. And if my acceleration is positive, then F net is positive as well. If my acceleration is negative, F net is negative as well. That is in terms of like the whole overall F net equals ma. So with that being said, right, for here we have friction. So when we're pulling this cabinet, based on, once again, the context of the problem here, we're also assuming that she's just pulling it across the floor. This thing isn't levitating and it's not sinking through the floor, right? So to start off, we should kind of think about this thing as only moving across the horizontal x direction, right? So our net force is either going to be negative x or positive x direction, right? It's either going to be moving net to the left, or the net force is going to be net to the left or net to the right, basically, right? We're not going to have a net force in the y directions because this thing isn't sinking and it's not floating, right? Now, what other forces do you see acting on this cabinet besides tension and kinetic friction? Yep, we have normal force. Okay, I gotta stop using this eraser. Whenever you guys see like what's written underneath is that I don't have like a blank sheet of this quiz and I don't know how to like blank it out without just literally just drawing it in white or putting a shape that's white above it. So forgive me for that. But here's normal force, and then we also have gravity, right? And by the convention of our free body diagram, if there's no net force in the y direction that we're assuming, right, because this thing isn't sinking or it's not levitating, so our Fn vector should roughly equal the size of our Fg vector, right? So these two vectors should be opposite each other in direction but equal in magnitude. So this should be like, for example, this could be, I don't know, well, if we're going by the mass, right, if 60 kilograms, right, the force of gravity, Fg, is equal to mg, this is 60 times 10, that's meters per second squared, so that should be 600 newtons downwards. This should be 600 newtons upwards, for example, right? So those should cancel out, and now we're just left with these forces here that are going to determine our net force. And you gotta draw them kind of proportional or in accordance with what the problem is saying, right? So if I'm slowing down at this rate of 2 meters per second squared, and like I said, that F is equal to ma, F net is equal to ma, if my acceleration vector is positive, like how I, observed in the context of the problem, then my net force is positive. So my net force should be pointing in the positive x direction. Therefore, this vector should be longer than this vector. So my kinetic friction should be overwhelming my tension force. Because if this is bigger than this one, if this was 600 newtons to the right and this was 500 newtons to the left, right, then it's an F net of 100 newtons, for example. So it's a net 100 Newton force to the right, basically. So does that make sense overall for the drawing of the free body diagram and making sure it's lining up basically with the context of the problem? Yes, it does? Okay, awesome. So next step is determining the magnitude of the net force on the cabinet, right? So net, let me actually go back to, I like the red color. F net is equal to ma, right? So for this F net force, we know that our mass is 60 kilograms and our acceleration is that 2 meters per second squared, right? So then our net force here should be 120 newtons, right? That's a very, very simple, easy 2 points right there. Quiz tip, if you literally don't know what any of this means, like if you don't know what net force is or how to calculate it or whatever, but you like look at your equation sheet and you're like, okay, well, net F net, that must mean net force, or just write this equation down, you're bound to get like at least half a point maybe. So write down as much as you can for the problem, even if you have no idea what you're doing. It helps. Trust me, there's times I've done it. This comes from personal experience. So just write anything down. Like if you have no idea what you're doing, just write something down. And if it's remotely related to anything physics, and it kind of makes sense, sort of, in the problem, then you're good. So you should at least attempt to draw something or write something down that's remotely physics related to gather some points here and there, because it happens to all of us. You're probably going to lose points one way or another, somewhere here or there. Obviously, we don't like to lose points, so if you can get 100 on all the quizzes and exams, awesome. If not, this is the way to maximize your points. So there is our magnitude of the net force, right? So for magnitude here, say for example, you screwed up and you said, okay, well, acceleration is negative, right? Well, it doesn't matter at that point. You could very well have misunderstood the context of the problem at the beginning, but if they're asking for magnitude here, just make sure your acceleration is positive, because regardless of what direction, what the context of the problem is, magnitude indicates absolute value. So you could literally just say, okay, well, F net, absolute value of that, is equal to mass times the absolute value of acceleration, and then you're golden, right? So there, that's part B. Make sense for everyone? If they're asking for the magnitude of the net force, if they're asking for the magnitude, then it's the absolute value. If they're asking for the net force, then you would have to indicate direction. So like, for example, if this A was -2 based on the context of the problem, right? If it was -2, then you would have to include that -2, and your force, in order for you to get the correct answer, you would have to say -120 newtons. Yeah. Same thing for like force of gravity, right? If they're asking what's the magnitude of force of gravity, right? You would just take 60 times 10 meters per second squared. Now, if they just said what's the force of gravity, I would multiply 60 times -10, right? Because that acceleration has to add up with the direction and the context of the problem. So if this thing is pointing in the negative y direction, best believe I should have a negative in front of that acceleration vector to make it -600 newtons. So there's that for part B as well. Part C now is finding the magnitude of the friction force on the cabinet, right? So, like I said, none of this crap here matters in the y direction, because we're only focused on what's going on the x direction. Because once again, this thing isn't levitating. This isn't Harry Potter, and it's not sinking through the floor, right? It's not possessed. So, in that case, we're only focusing on the net force in the x direction. So we're concerned with our component of the net force in the x direction. So I have a question here. It says, if the question asks for magnitude of net force, will we always use the F net equals ma formula? Whenever we're talking about net force, you're always going to be using F net equals ma. Now, if they're asking for magnitude, magnitude just means the absolute value of that net force. So if I were to ask for the magnitude of gravity, right? If I was asking for the magnitude of the gravitational force, I would then not include a negative sign in front of that acceleration vector and just do 60 times 10 equals 600 newtons. If they were asking just what is the force of gravity, for example, right? Then I would have to include my directions. Now, regardless, if they're asking for net force indicates that you're going to have to set up some kind of equation where F net equals ma is involved. If you're that's in terms of like usually finding like one force or something. But if you have an example like part C here, where you're trying to figure out this friction force, right? But you also have other forces in the x direction that you want to figure out. So we know Ft, but we don't know Fkx, for example, right? Then you would have to set up a whole like F net x component equation, right? And that's still equal to ma, and that would be max because this is the x direction. It's just that now you're also setting it equal to the forces that make up that net force, basically. Does that make sense? Okay, cool. Yeah, I mean, just basically what it means is like these two forces are going to be contributing to the net force. The net force is always going to be equal to mass times acceleration. But I want to figure out, okay, how does this mass times acceleration come into play? How does that occur relative to all these component forces? So in that case, I have to write this F net X total equation, right, to figure out the component parts, basically, right? So I would do, for example, Fkx, that's pointing in the positive X direction. And this is something I repeated multiple times throughout my last homework review session, is how to set up this F net X or F net Y equation with signs or without signs, with indicating direction or without indicating direction. So if you did watch my videos in detail, which I hope you did, but I understand if you didn't, just because they're long. So basically the gist of it is I personally prefer to integrate the directions of my forces right then and there. So if I see that this is pointing in the positive direction, this is going to be positive in my F net equation. If I see this F tension force is negative, I'm going to include a negative side in my equation. So for my F net X, my net forces in the X direction, I would set it up as Fkx minus Ftx. Now, a lot of the times your professors will do Fkx plus Ftx, for example, right? So plus or minus doesn't matter. It just kind of tells you what you need to put in for Ftx. So what that means is, okay, so if I have this Ft, right, if this was the 500 newtons, right, I know that 500 newtons to the left, if I were asking for what is the net force for, or if I asked you, what is the force of tension here? If I just asked you, what is the force of tension? Can someone give me a value for that? Exactly, right? So that's negative 500 newtons. I would integrate the direction right then and there. Negative 500 newtons is the direction of the F tension force, right? Now, if I choose to do it this way, where I do Fkx minus Ftx right then and there, right? All I have to do, if I integrate my directions from the begin with in my equation, all I have to do is just input the magnitudes of all the forces. So if this was, let's say, Fkx minus Ftx minus another like F pull minus another F push, right? Or add them up, right? If it was minus F pull plus F push, for example, if it was pushing in the right direction. Basically, all I have to do, since I'm integrating my directions right then and there, I just plug in the magnitudes of everything. So if this was minus F push, right, I would put in the magnitude of the F push force, right? So what that means is, if this was the negative 500 newtons that we said, right, if I include this negative sign, then I just have to put 500 here, right? Because you'll literally, the negative sign is taken care of. So minus, and then you just throw in the 500, you're left with minus 500. So it makes sense, right? Now, if I put the Fkx plus Ftx, then I have to be sure to include the direction. So if this was Fkx plus Ftx, then I have to say, okay, this is plus a negative 500 newtons. So I have to indicate the direction that way. They're the exact same answer. You'll get the exact same result. It's just whether or not you choose to indicate the negative signs from the begin with in your equation or not. The reason why it gets kind of a little dangerous, right, is that you could very well put this negative sign and then put another negative sign here on accident, right? Because you were thinking, okay, well, Ftx is negative 500 newtons, right? We determined that. That's absolutely correct. It's negative 500 newtons. That would be the tension force in the x direction, right? Because it's negative x. It's pushing to the left or pulling to the left, right? If I throw another negative, this becomes overall positive. That's not right, because that would indicate that that tension force is pointed to the right. So that's why I have to be a little bit careful. If I throw in my negative signs here, it's just easier, because then I can just put in the magnitudes of everything. I included the negative signs based on the direction that I see in my free body diagram. Otherwise, if I do plus Ftx, I have to watch out to put in the signs here. And it just gets kind of icky. So if I have the negative, minus, plus, whatever, I just throw in my magnitudes of all the forces, and the directions are right then and there with the equation. So if I have this Fkx, for example, and this minus Ftx, I would just throw in 500 here. I wouldn't do negative 500. I would just throw in 500 newtons, right? So I just throw in the magnitude. And by magnitude, we mean absolute value. So there's your 500 here. That's your magnitude for the F tension force. And this negative sign already indicates the direction built in. And so then we have MAX, right? We already figured that out to be 120 newtons, right? So this is 120 newtons is equal to FKX. And this is minus 500 newtons here, right? And then we can easily just do some algebraic manipulation to figure out that this is 620 newtons for our kinetic friction force. Now, if you were to have done this problem, if they were, for example, to ask you what is the net force, not the magnitude, and you so happen to think that slowing down at a rate of 2 meters per second squared meant a negative 2 meters per second squared, and you ended up with a negative 120 for your answer here, that throws everything off, because then you have negative 120 and you add up a 500 here, you would end up with like 380 newtons for your answer for FKX. And if FKX was 380 newtons, if this was 380 and this is 500, well, this force is greater. So not only is your free body diagram then incorrect, it also doesn't match up with the context of the problem, because despite the woman pulling directly to the left, she's slowing down. There's some force that's overwhelming her, and that's the force of friction due to the carpet. So your free body diagram has to add up. You have to show that that kinetic friction force is overwhelming the tension force. So you have to draw the FKX longer than the FT. And you have to make sure that your interpretation here, if they were to ask you just for the net force and not the magnitude, if they just asked you what net force is, you have to make sure that that acceleration vector is correct, has to match up with the context of the problem. So if I was moving to the left with a negative velocity and I'm slowing down, then slowing down means that my velocity and acceleration vectors are in the opposite direction. This is a throwback to like the first 2 weeks. So then acceleration is positive. If I throw in an acceleration positive here, I get a positive 120 newtons. I put that into my F net x equation. That's equal to the MAX portion. And then I just make sure that my setup here, if I do FKX plus FTX or FKX minus FTX, that things kind of make sense. So if this was minus here, I integrate the direction already. I just throw in the magnitude here, just a solid 500 newtons. If I were to put a plus sign, I have to make sure that I'm doing, okay, plus negative 500 newtons, which just by math rules is the same thing as minus 500, which is what you see here. I personally prefer to throw in the negative sign right then and there. It just gives me a sense of direction. I can visually see I'm pulling to the left, that's going to be in the negative x direction. If the friction is pushing to the right, that's going to be the positive x. So I throw my signs there in the equation from the begin with, and that just keeps things simple. Because otherwise, if you kind of mess things up, you could put in minus negative 500 newtons on accident, right? And that could end up with a positive 500, and that's not right because, like we said, she's pulling to the left, so it has to be negative x. So if you just throw in your magnitudes, if you indicate your signs here from the begin with, throw in your magnitudes, make sure that your net force here is matching up with the information, the context of the problem, you should be able to, well, there we go. You should be able to get, okay, all right. You should be able to get your correct kinetic force at the very end. So, does that all make sense for part 1? I try to kind of go over the whole direction thing again because it seems very trivial, but trust me, like I've seen people lose points on so many points on an entire problem for messing up the directions, throwing in an extra negative sign here or there on accident, or forgetting to indicate direction or whatever. So just be really sure that you're matching up your equations to the context of the problem, throwing in the correct signs where they need to be, choosing one system and going with it. So if I'm adding up all the forces, I have to include negative signs to indicate the direction. If I want to indicate the direction from the begin with, just throw in like FKX minus FTX minus F push minus F pull, whatever. then I just throw in magnitudes. Pick a system, stick with it, make sure it matches up with the context of the problem. So hopefully that makes sense for problem 1. Any questions at all? Mm-hmm. Yeah, so I don't automatically upload them to the Google Drive, but sure, yeah, I can upload them from now on for sure. Um, and I'll upload the previous, yeah, I can upload the previous ones as well, so you guys have access to that when you're doing your a final exam review or whatever. So yeah, I can make these available for you guys to look over again. But otherwise, they're uploaded like to the Google Drive and YouTube, just the review sessions. But yeah, I can make these documents available for you guys to look at. No problem. Mm-hmm. Any other questions about problem 1? Mm-hmm. Yeah, so that's a great question. There are a couple different friction forces. I'm not sure who you have for your professor, but um, for the lecture slides for Dr. DeJong, he goes really in depth with all the different types of friction forces. Um, but just for now, FKX indicates kinetic friction. Kinetic friction refers to friction forces as a result of an object sliding across a surface. So if you have this cabinet, it's sliding across this carpet floor, right? That's kinetic friction. So kinetic friction, think of a sled sliding on an ice rink, for example. That would be another example of kinetic friction. So an object sliding across a surface. For FS that you were referring to, that's static friction. So static friction is a little bit difficult, I guess, to understand for some people because there's different contexts where you'd think it'd be applied and it isn't and whatnot. And we'll get a lot more in detail with the whole static friction force thing in the next couple of weeks when you do centripetal motion. But for the static friction force, I usually think of that as the friction force that keeps an object from slipping. Right? So if, or alternatively, you could also think of it as basically the friction force that kind of, to a certain extent, keeps an object at rest, sort of. So basically, and we'll get into this a lot more in detail, but if I were to push on this box, for instance, right, there's a certain amount of pressure, I'm going to say pressure, there's a certain amount of force that I have to apply before that thing starts moving, right? That certain amount of force, right, that threshold, let's say, for example, this box doesn't start moving until I push it with 600 newtons of force, right? That 600 newtons of force is the amount of force that I need to put in to overcome static friction. Static friction would then, in that case, just be like the amount of friction force that's going to need to be overcome to begin moving that object, basically. That's another way of thinking of it as well. So it kind of depends on the context because, like I said, in the next couple of weeks, we'll get into centripetal motion, which is like just circular motion, right? So static friction force is also the friction force that keeps tires from slipping on a car, right? So if you're turning, for example, at an intersection, let's say, let me draw an intersection real quick. If you're at an intersection, you're turning, static friction force is pointing radially inward if we're moving kind of like in a circular type motion, because if you're moving that way, it's kind of a circular type motion. So once again, this is a couple weeks ahead, but static friction force would just be the force that keeps an object from slipping. and is basically the amount of friction force that needs to be overcome to kind of get an object moving. We don't really get into that right now with this chapter. I would just kind of refer to this at the moment. Kinetic friction forces as a result of objects sliding across the surface. Static friction force that keeps objects from slipping, right? There's not slippage here at all, right? Because this thing is already in motion. So if we're already in motion, static friction force is not applicable anymore. If you're already in motion, static friction force is not applicable in terms of an object sliding across the surface. Now, like with that example, with the car turning at an intersection, right? That's a little bit different, because then at that point, it's the force that is keeping you from slipping. So, I mean, that's, like I said, this is a couple weeks away, but there's also rolling friction. This is almost never used, and that's just friction due to or I'll say like friction in the context of wheels or tires or something that's moving. And it's usually negligible, like even with getting into centripetal motion with like cars and stuff, and if you have like a cart, for example, and you're rolling that cart around and it has wheels or tires or whatever, we very rarely ever integrate rolling friction. So like wheels, for example. So yeah, I would focus mostly on the kinetic friction aspect, just because that's the context of this problem here is an object sliding across the surface. Static friction force keeps an object from slipping. And then rolling friction is just friction with respect to like wheels or any circular type objects, balls or whatever. So that's very rarely ever used, the rolling friction. I don't think I ever saw a problem, maybe one, the entire year of 131 when I took it, that we ever integrated rolling friction, but it's mostly negligible. So hopefully that kind of makes sense with the indication of all three types of friction forces. Mm-hmm. So if this was speeding up, then this tension force is going to be overwhelming the kinetic friction force. Yeah. Because if it was speeding up, then since I'm moving to the left, it's negative velocity. If it's speeding up, then my acceleration and velocity are in the same direction. So there's going to be a net force to the left because I'm overcoming that kinetic friction force from the carpet. And so my F net x should actually also be negative because I'm moving net to the left. Does that make sense? So yeah, this is slowing. Yeah, this is slowing down because if I'm moving in the negative direction, I have a negative velocity, right? And if it's slowing down, right? Slowing down, this kind of goes back to the first couple of weeks. Slowing down means that your velocity and acceleration vectors are on the opposite direction. So I'm moving to the left, acceleration is to the right, slowing down. Now, if, like you said, if your tension force was stronger, right? If you were speeding up, then your negative velocity, and then you have a negative acceleration that would give you a net force to the left. But we're slowing down as well because obviously it says here in the problem that slowing down at a rate of 2 meters per second squared. So if you're slowing down, then there is some force that is overwhelming your tension force, and that force is kinetic friction. It's giving you it's giving you a net force to the right. Yep. Mm-hmm. All right. Everything else okay for problem one? Okay, I can. It's kind of tough to hear you. Okay, I don't know if it's my mic or not, but I can hear my voice too, like it's kind of echoing. I don't know if you want to try the chat too. I'm sorry. If someone else heard her as well, like, please let me know. Can you explain the subscripts? Yeah. Just the subscripts within the context of this problem, or subscript, like the whole idea of subscripts in general? Because with regards to the subscripts, it's just a matter of identifying what force is acting on the object. And then, so if we're looking here at gravity, gravity is always pointing downward, so we just assign a little g for the subscript to indicate the force of gravity. If we're looking at a friction force, we have to indicate what type of friction force it is. Since this is objects sliding across the surface, we put a little fkx to indicate that this is the kinetic friction force in the x direction. And for tension, we just put a little t to indicate tension force. Normal force, we put a little n there to indicate the normal force. Yep. For part B, are we always going to use F net equals ma formula if a question asks for the magnitude of the net force? Yeah, you're always, if we're asking about net force, you're always going to do F net equals ma. Whether or not you indicate a negative sign comes down to the magnitude. So if it asks for magnitude, everything should be positive. If it asks just for the net force, you keep this whole F net equals ma the same. It's just that you have to indicate the direction somehow with a negative sign or a positive sign depending on the direction of the acceleration vector. Sound good? You would change it to negative depending on the direction of the acceleration vector. So like I said here, if this is moving, if we're pulling the box to the left, left indicates negative x direction. Since we're slowing down indicates that your velocity and acceleration vectors are opposite each other. So if I'm pulling left, negative velocity, negative x, right, negative x direction, then if I'm slowing down, my acceleration has to be in the opposite direction, positive. If I was speeding up, they have to be in the same direction. So if I was speeding up, moving left, then my acceleration is also to the left. So directions of acceleration are just dependent on whether you're slowing down or speeding up and relative to your direction as well. So if I have a net force to the right, then I have a positive A. If I have a net force to the left, I have a negative A. That just means that there's a net force to the left or a net force to the right. And you would have to adjust your acceleration value or sign based upon that. So it just kind of depends on the context of the problem. Since we're pulling to the left and slowing down means that your velocity and acceleration are opposite each other. So this was negative velocity, acceleration is positive. If we're speeding up, negative velocity, then acceleration would be negative as well. Got it? Okay, cool. Just for sake of time, I'm going to move on to problem 2 now. And if anybody else has any questions about problem 1, we can try and answer them at the end. I just want to make sure we get through everything. And so for problem 2 here, we have a suitcase. A woman is towing her suitcase by pulling on a strap at an angle of 58.11 degrees above the horizontal. It says we need to draw a free body diagram below of all the forces acting on the suitcase, assuming friction is not negligible, and then label each force vector with the appropriate subscript. So we can draw a little Cartesian plane here, positive y, positive x coordinates, right? And then we want to look at all the forces that are acting on the suitcase, right? Anyone want to name forces? You guys can shout them out, and then we'll figure out if we're missing anything. Yep. How would the tension force be pointing on the, if we're pointing upwards, downwards, what? Yep. And so we'd have up and to the right, because kind of based on this problem here, up and to the right at an angle of 58.11 degrees, and that's from what? Above the horizontal. So this is the horizontal, above it, like that, 58.11 degrees. This is our F tension force, right? And then what else other than F tension? Yep, excellent. Kinetic friction. Let me try and do a different color here just to kind of differentiate. This is FT, or FT, and we have kinetic friction, right? What else? Yep. Okay, there we go. Force of gravity. And what's the last force that we should have? Yep, normal force. So now, based on the context of this problem, do we have any indication that this thing is moving in the y direction at all? Like, just think of yourself pulling your luggage in an airport. Do you think this thing is going to be levitating or sinking through the floor? No, right? We're not casting any spells on it. So just kind of using our physics intuition and knowledge of the world, our F net y from the beginning with, we can kind of assume that it's going to be 0. That's a pretty safe assumption there. And if we're just dragging it across the floor, our net force is just probably going to be in the x direction, right? Rolling friction. So rolling friction, going back to kind of what I said before, it's sort of applicable in the sense that you do have wheels on luggage normally. It's just that that type of friction, especially regarding rolling friction, for some reason in physics, it's just negligible, like 98% of the time or 99% of the time. I really don't have like a solid, better explanation for it other than we were just really told that it's not applicable in most cases. I feel like it's just, I don't know, honestly. Unfortunately, I don't have a better answer other than that it's generally not applicable when you're calculating your friction forces. Unless they require you specifically to indicate rolling friction, we almost never use it. So I would just stick with the kinetic friction force because like you can kind of think of those wheels kind of sliding across that surface. Yeah, unfortunately, it's kind of take it as it is for the most part. If I find or understand a better explanation as to why we usually don't include rolling friction, like I tried asking why, and we usually just got the answer that it's just not applicable. We don't have to worry about it, and that's the end of it. So maybe I'll just do a little bit more research on that and get back to you guys on that one. But yeah, there's honestly you almost never use rolling friction. But yeah, I mean, technically, yes, rolling friction is applicable. Like in real life, it's a thing. It's there. It exists. But yeah. Or I guess think of it as if your wheels, right, got jammed on the luggage, right? If these things got stuck and you're just sliding across the floor at that point, then that would be kinetic, directly sliding. You could, if you wanted to, label this as rolling friction instead of kinetic friction. Doesn't really matter. It's just, I guess, we usually don't refer to this, or we usually don't use or label or indicate rolling friction in our problem. So we usually just default to kinetic friction if we have an object kind of sliding across the surface. Technically, it would be rolling friction, but like I said, it's just we almost never really use it. So, but yeah. I think that's about it for the forces here: FKX, FN, FG, and FT. So yeah, any other questions about this free body diagram here? Well, oops. Anything? kinetic friction is a friction force. So if there's no friction at all, then this wouldn't even be here. It would literally, the only thing that would be contributing to, like if this was a completely like slippery surface with no friction whatsoever, the only force that would contribute to the motion would be that the X component of the tension force. Does that make sense? But yeah. Any other questions about the free body diagram? Nope. Okay. I will move on to part B then. So part B wants us to determine the net force in terms of components, given that the suitcase weighs 27.5 pounds, that the force from the surface is 23 pounds, that the force of friction is 2 pounds, and that the woman is pulling with a force of 5.3 pounds, right? So when we got this quiz, everyone tripped up because, yes, pounds is a measurement of force, technically, right? So everyone thought that they had to convert pounds to newtons, basically, to figure things out. But as long as all your units are consistent, right, everything here is in pounds, you really don't have to. So you can just go ahead and calculate your net force in pounds. So they might trip you up on something like that. Usually they don't. But if we want to figure out F net x and F net y, we have to set up those equations again. F net x, right? So we have what force is acting in the x direction here. So there's friction, right? So Fkx, and then what else? Yep. So once again, okay, so this is Ftx right here. So I'm going to indicate things with the direction. So I have Ftx, that's pointing right. Fkx was pointing to the left, so I'm just going to include that negative sign at the start, minus Fkx, right? Ftx minus Fkx, that gives me my net force in the x direction. And then I also have my F net y, and what would the forces in the y direction be? So I heard gravity and I heard tension force. Yep. So there's gravity and there's the Fty, right? The y component of the tension force. And then what else? Yep, normal force. And so I'll indicate direction from the begin with the equation as well. So I have normal force pointing upwards, Fty pointing upwards, and then minus Fg, because Fg is pointing downwards, right? So I have all those, I have both equations here set up. So I know that the suitcase weighs 27.5 pounds. What does it mean when something weighs a certain amount? When we're talking about weight, what is that an indication of? Yeah, you're kind of on the right track, right? So it's that's going to be your force of gravity, right? So if you have force of gravity equals mg, that's technically your weight, right? So in this case, your weight would be the 27.5 pounds, right? So when we're talking about weight, weight is going to be equal to mg, basically, right? Now, we can't directly calculate for, like if they ask you for mass or something, you can't just go ahead and divide by 10 and get your mass, because this is pounds. So you would have to convert that to newtons. There's a conversion factor. I can't remember exactly what it is. It's somewhere on the slides and I can pull it up later, but there's a conversion factor to go from pounds to newtons, and then you would divide by 10 meters per second squared to get your mass. But for now, since everything is in pounds like they have it in the problem, we're just going to stick with pounds. And we know that our weight is equal to Fg. When we're talking about weight, we're talking about Fg. Now, force from the surface is 23 pounds. What does it mean when we're talking about force from the surface? What is that an indication of? Yep, awesome, right? Normal force. Does anybody not understand why the weight from this, or the force from the surface, is classified as the normal force? So the force from the surface, they said it's 23 pounds. We said that that is equal to the normal force. So when we're talking about force from the surface, that means normal force. The reason why is that the normal force is defined as the force that is going to be perpendicular to the contact surface. So if this is our contact surface, if this is the floor, it's the force that is perpendicular, right, forming a right angle with the surface, as well as the force that pushes up or just pushes against an object, right, to give solidity to the contact surface and prevent, and this is very informal, so preventing an object from sinking through the floor or moving through a wall, for example. So in this case, the suitcase is right there, right? I'm exerting some force of gravity downwards. There's a force that is exerted from the surface or by the surface to keep that suitcase kind of at that level of the floor. Because otherwise, if the force of gravity is greater than the normal force, then this thing would be sinking down. So normal force is the force here that is from the surface, or the force that the surface exerts on the object. Make sense? Mm-hmm. And then force of friction is 2 pounds, right? So we have this FKX is 2 pounds. And the woman is pulling with a force of 5.3 pounds, right? So the F tension force is 5.3 pounds. That's overall, right? That isn't FTX or FTY necessarily. It's just that this FT is 5.3 pounds. So if we want to figure out all this relative to these equations here, figure out F net x first, how can we figure out FTX? No, you're fine. Yeah, the tension force, again, was the 5.3 pounds, and you're absolutely right. We can use cosine 58.11 and multiply that by the force of tension to get our FTX here. And the reason we use cosine is that it's adjacent. This is the FTX, adjacent. So adjacent means next to the angle or touching the angle, divided by hypotenuse, right? And our hypotenuse is our F tension force. So FTX over FT should be equal to cosine 58.11. We can multiply the FT over. So that's what, 5.3 pounds times cosine 58.11, and that should give us our FTX. And I believe that is around 2.8 pounds, if I'm not mistaken. Someone correct me if that's wrong. So that's 2.8 pounds, and then you have FKX, right, where we already determined that to be 2 pounds. So we can just plug in the magnitude of that, right? That's just 2 pounds right then and there. Technically, if we're just looking at what this would be, FKX, what should the force of kinetic friction be? Yeah, if we're looking at, if I just asked you what is the force of kinetic friction here, what value would you give me? Oh, so my bad. This is pounds. Sorry, I made that mistake. This is pounds. But you're -2. Yeah, because it was where is it? Yeah, force of friction is 2 pounds. I just for some reason I just brought the L a little bit close to the 2, so it looks like 21. But yeah, you're absolutely right. It should be negative, right? It should be negative for that force of kinetic friction there. But like I said, since I'm integrating the direction within the equation itself, I'm putting that negative sign. I can just throw in the magnitude, like I said earlier. So it's just -2. Otherwise, if I had FTX plus FKX, then I have to throw in a -2. So for my F net x, I should get somewhere around 0.8 pounds. Let me write it a little bit farther away so it doesn't look like 81. 0.8 pounds for my F net x. Now for F net y, I have my normal force. We said that was 23 pounds. Plus my FTY. How can we get FTY? Yep, exactly. So sine of 58.11 degrees times our FT, and the FT was what, 5.3 pounds? Yeah, so 5.3 times sine 58.11 to get FTY. And that's because FTY here would be opposite the angle over hypotenuse. So FTY over FT is equal to sine 58.11 degrees. You multiply the FT over FT times sine 58.11, that gives you FTY. So you just do 5.3 times sine of 58.11, and that should give you around, I think around 4.5 pounds. And then finally for our force of gravity, we already know that force of gravity means weight, and they said that the suitcase weighs 27.5 pounds. So I can just automatically just throw in 27.5 there. I just throw in the magnitude, right? If I were asked about the force of gravity just in general, they were wanting me to define the value for force of gravity, not the magnitude, just the value of the force of gravity, I would have to say it's negative 27.5 pounds, for example. Or if it was in newtons, right? If it was like, I don't know, 600 newtons or something, right? Then I would say it was negative 600 newtons. That's if they're just asking for the value. If they're asking for the magnitude, then I just take the absolute value. So I make everything positive. But I'm integrating the direction here, so I can just throw in that 27.5. And then if I find the F net y here, 23 plus 4.5, that's 27.5, minus 27.5 pounds, right? We should get 0. And that confirms, that's our sanity check, right? At the beginning of the problem, we thought, okay, well, if this thing is being dragged across the floor, 9 times out of 10, unless you're at Hogwarts, it's not going to be levitating, it's not going to be sinking through the floor. You're not going to have any net force in the y direction at all. It's just going to be straight up across the x axis. So if by any chance you get something other than 0, and like you have any sense of how the world works, you should go back and check your calculations, because you could very well have done, like, if you had this negative sign and you throw in an additional negative 27.5, for example, or if it was a newtons, for example, if it was 600 newtons, and that's negative 600 newtons because it's the force of gravity, so it's pointing downwards. If you threw an extra negative sign, you might have gotten positive 27.5 or positive 600 newtons or whatever it is. And so in that case, it would be 27.5 plus another 27.5, and that would give you a net y force, right? So that would mean this thing actually would be levitating, and that doesn't make any sense. So that's your sanity check. If it's 0 newtons, it makes sense within the context of the problem. But yeah. Sound good? And I guess another thing is you can kind of also check back with your calculations to make sure that your free body diagram also is proportionate, because let's say, for example, here, if you were to have your FKX, right, be equal to your FTX, then that indicates that there's no net force in the x direction if they're the same size. This one has to be a little bit longer than this one, right? To indicate that there's a net force to the right. Now, here I actually have to adjust my normal force a little bit, right? Because based on the information in this second part, they said what? That the weight, or the FG, was 27.5, but the normal force, the force from the surface, is 23. So this normal force actually has to be a little bit smaller. So it should be maybe about this size or something, or a little bit like that. So you can go ahead and kind of like edit your free body diagram roughly based on your calculations. That's kind of a risky situation, because if you did your calculations incorrect, then you could go back and edit your free body diagram. That could mess things up even more. But generally, like, if you have the correct directions and everything, they're not gonna like grab a ruler and like look, okay, well, this is, you know, 5 centimeters or this is 4 centimeters or whatever, and then just kind of like nitpick about your length of your vectors. But if you roughly kind of have things in the right direction and it kind of looks about right in terms of the proportionality of the vectors, you're okay. I wouldn't dwell too much on the length of the vectors unless there's like a huge difference. Like if this was 10 pounds or something and this was 27 and a half, then yeah, you definitely have to edit that to be smaller. And so what you realize here is that this is smaller than the FG, but since there's also an FTY, the FTY plus the FN, they add up to make, or to cancel out the force of gravity. So that's what we see here, right? So there's 23 pounds from the normal force. There's 4.5, right, from the tension in the Y direction, and they add up to cancel the weight of the suitcase. But yeah. And then with regards to the rolling friction thing, I mean, kind of looking back at this problem, you could, if you wanted to, label this as rolling friction because we definitely have wheels. So if you wanted to, you can say rolling friction, I guess. But like I said, it's just, I don't know what the physics like teachers and what this course has against rolling friction, but like it's almost always kinetic if we're having like an object sliding across the surface or moving across the surface. It's very rarely rolling friction. So like 9 times out of 10, I would just put kinetic friction there. In this case, since like obviously it's a suitcase and it's rolling across the floor, you could, if you wanted to, put rolling friction and that's acceptable. I think that's also something that the professors pointed out the year I took, that you could have put rolling friction if you wanted to. It's not wrong. It's just that in most cases we use the kinetic friction kind of concept as opposed to rolling friction. For FTX, the 2.8 pounds is a result of cosine 58.11 times your FT. Your FT was 5.3, so if you take 5.3 times cosine 58.11. I didn't write out like the whole cosine sine trigonometric calculations just because it would have taken too much space, but actually, you know what? I'll just write them here out on the side for. So if we have FTX, that's equal to FT times cosine 58.11, 5.3 times cosine 58.11, and that's equal to 2.8 pounds. FTY is equal to FT times sine 58.11, and that's 5.3 times sine 58.11, and then that's equal to, what was that, 4.5 pounds. Yeah. Sound good for FTX? At least I hope the value is correct. If someone wants to check and let me know if I mess something up, please do. But sound good for problem 2? Any other questions? Does a 2.8 make sense, Zainab? Cool. Yep. So that's the quiz section of tonight's review. Now, if there aren't any other questions about anything regarding problem 2 or problem 1, I can kind of move on to pinpointing some important problems in the online written homework, and I guess picking out some important slides to go over and stuff from the lectures. So is everyone ready to kind of move on to like the I guess tips on what to study and stuff? Yes. Okay. Awesome. So that's the gist of quiz 3 review. I'm going to be uploading this document to the Google Drive as well, so everyone has access to that. But for now, we can kind of, I'll move on to the online homework first. So I want to see here, just kind of flip through it. This big section here, I mean, offers some good conceptual stuff. I would say this is going to be more important for like the exam on building concepts and conceptual understanding, but for the sake of the quiz, I wouldn't worry about it too much. If you have like a significant problem with these, please let me know if you want to review a specific one. But yeah, I wouldn't like dwell too much on like this part here because, like I said, the quiz is very reminiscent of the written homework stuff, and it's very rarely like concept heavy. So, no, go ahead. What's that? Oh, if you want to take a screenshot, yeah. Mm-hmm. Okay. Um, yeah, and I'll go over Newton's third law here in a sec. But with regards to vectors, I give this maybe like a 2-3 minute review real quick again, just because like we've already done this the past couple of weeks, the vector addition and stuff, so I wouldn't dwell too much on it. Um, that's assuming you have a decent understanding of the whole vector stuff. Let's see here. What else should you review? Acceleration. That one's okay. Let me see here. Let me read this problem real quick. So, traveling along a straight road at a speed of 20 meters per second. 2 seconds later. Okay. Yeah. This isn't like too heavy. This is a very simple problem. It'd be nice to kind of go over this one in terms of like just building your mathematical understanding of FNet equations, acceleration, stuff like that, but that isn't the greatest practice problem in my opinion. This one is, though, problem 4 for sure, because I can very well see that they could throw in net force stuff and then bring back some of the earlier concepts. So I would still make sure that you kind of know your kinematic equations. I think they should offer you an equation sheet with the kinematic equations on there, but I could see them maybe giving you a net force or something like they have here, figure out the acceleration, and then you have to throw that in to figure out some other variable. In this case, they wanted you to figure out displacement, for example. So I'd say this is a very good example to kind of go over because it gives you a sense of not only this week's concepts, but reinforcement of past week's concepts. Let's see here. This one is still kind of very basic as well, problem 5. It's just kind of plug and chug. This is just if you want to review your math, but it isn't testing on your understanding necessarily of how to pull information from a problem, because they're basically giving you all these values here. They're giving you mass, they're giving you acceleration, so you just go ahead and figure out net force, and then here, for example, right, they want to ask acceleration produced by the same force when acting on a mass of 1 kilogram. So this is just mathematical manipulation. Once again, if you need practice with that math, problem 5 would be a good one. But in terms of like reinforcing concepts, it isn't the greatest. This longer problem definitely is, though, because it does a little bit of the vector addition. It does a little bit of the net force stuff, right? And brings back some of like your trigonometric functions and figuring out directions from the past week stuff. So I'd also go over this because I could see them maybe throwing in a problem about net force. Might want you to, factor in like, okay, Fnet plus Fnet y plus Fnet x, and then figure out the net force overall, figure out the direction, stuff like that. So this would be a very good problem to go over to bring multiple weeks concepts into focus. This is also another kind of like conceptual one. This is actually, I'd say this is very, very important to go over too, because it kind of gives you a sense of how to identify all the forces, because you might be really good at identifying one force and then forget another, for example, right? Because in this case, you obviously have normal force, gravity acting on each person on the skateboard, right? You have a tension force by the student on the right, but for example, you have this kinetic friction force too, right? Because it's kind of, you're sliding, right? Or you're kind of holding onto that rope and it's sliding between your hands basically. So yeah, so I'd say this is a good example too to kind of reinforce some concepts and how to identify all the forces that are acting on objects. If you have trouble understanding normal force, I would say this is, or not normal force, I mean, yeah, so this is actually like, okay, this is a good example here of the action-reaction pair stuff. So let me kind of read it real quick. So it says, when the swimmer exerts a force on the wall denoted as force of feet on wall, she accelerates in the direction opposite to that of her push. This opposition is the result of Newton's third law of motion, which dictates that the wall exerts a force on the swimmer, denoted as F wall to feet, that is equal in magnitude, but that acts in the direction opposite to the force that the swimmer exerts on the wall. Choose a free body diagram for the swimmer that corresponds to the above situation. So you have this buoyant force, right, which is kind of opposing the force of gravity, kind of keep you floating, right? And we have the force wall on feet, right? So you push with your feet onto the wall, force of feet on the wall in the right direction. But then the wall kind of exerts that wall on feet force that's equal in magnitude, opposite in direction, right? So the force that you exert on the wall, the force that your feet push up against the wall is the same force, but in opposite direction as the wall pushes back on your feet. Now, someone might think, okay, well, why isn't it this, for example? Why isn't it this free body diagram, right? Well, if we think about it, well, these two cancel out. We're not moving in the y direction. We're just moving, across the x-axis, right? Well, if we also included this part right here, then this would indicate that there's no net force, right? That wouldn't make any sense because the swimmer is obviously going to the left. So we usually just include the force of the wall on the feet, or essentially like if your action was the feet on the wall, then the reaction is what we include. So, yeah. I mean, yeah, sure, I guess, but I don't think that would ever be possible because the wall can't, like, I guess, dictate necessarily. Or okay, oh, hold up. So I see what's going on here. So I didn't notice this. They actually have this notation a little bit backwards. In addition to the fact that this would be canceling things out. So this says feet on the wall, but the feet on the wall is actually this way. So this should be over here, and the wall on feet should be over there. So there's two things wrong with that notation, is the fact that this thing is canceling out, so there's no net force, and at the same time, they should be kind of switched around, basically. What's that? So I'm guessing that's just because they want you to kind of look at this as what force primarily is kind of acting on the swimmer here to give her that forward motion, right? Because, I mean, if we were wanting to look at the action reaction pair, then we'd include both of them. But in this case, we're just kind of focused on just the force that is that reaction, essentially. So we just want to focus on the wall to the feet. because it's like, I guess, um, let's see here. I want to think about it a little bit differently. So if you're, it's a matter of like, what are we concerned with? Are we concerned with like necessarily labeling that her wall to feet is the same as the feet to the wall? I mean, sort of, because that's an action reaction pair that's going to indicate what this magnitude of this force is going to be. But the thing is here is that we're just kind of looking at just the force that is involved in propelling the swimmer forward. So yes, there is a force here that should technically be there if we're concerned with looking at the action reaction pair. But if we're looking just at like what force is involved in giving her that net motion forward, then we're just looking at wall on feet. Does that make sense? Yeah, because I mean, like, we're trying to indicate that there's something that's pushing her forward, right? Because otherwise, like, this would make it out to seem that there's nothing that's pushing her forward. So, in terms of like identifying an action reaction pair, yes, we'd kind of have to like include both forces. But when like drawing a free body diagram and trying to calculate, okay, what's the net force that's kind of pushing her forward? In that case, we'd have to just basically focus on that reaction part of the action reaction pair, if that makes sense. So if I'm acting feet on wall, right, pushing this way, I'm not concerned about that because this wall isn't moving, right? I'm not, and it's not factoring into my, well, I guess sort of it sort of is kind of factoring into like your overall motion, because then whatever force you push on the wall with is the force that is equal to the wall pushing back on you. But like I said, we're just concerned with that reaction aspect. You know, what force that the wall exerts back on you that's going to allow you to propel forward. So that, in addition to the fact that they got these superscripts wrong, is why B is incorrect. Does that make sense with regards to the action-reaction pair stuff so far? And I think, I can't remember who had asked earlier. I think it was Amanda, but she might have left. Yeah, I think she left. But, I mean, I guess, yeah, hopefully that makes sense to everyone with regards to the action-reaction pair stuff. Yeah, and here it says massive swimmer, 65 kilograms. She wants to get an acceleration of 1.1. How hard should she push, right? So we're concerned with wall on feet, right? Wall on feet is going to be equal to the negative of feet on wall. So, or the opposite basically, right? So in that case, you know, she should push with a force equal to 71.5 newtons, for example, to the right. So she should push feet on wall with 71.5 newtons. And here I actually kind of solved it a little bit incorrectly, because if she's moving to the left with an acceleration of 1.1, right, then this 1.1 here should be a negative 1.1. And so then the negatives would cancel out and give you a positive 71.5. Otherwise, like, this negative sign here is a little bit incorrect with regards to the notation. But yeah, like I said, we're just concerned with, yeah, I can say that again. So force of wall on feet, right? Force of wall on feet, right? That's the force that the wall exerts back on your feet. That's to the left, right? Your force of your feet on the wall is pointing towards the right. Now, they should be equal but opposite. So if, let's say here, this is what? Wall on feet. And this is, feet on wall, right? So if I want to figure out how hard she should push the wall, right, that's an indication of trying to figure out the force of feet on wall, right? Because it's the force that her feet push against the wall with. So we're trying to figure out this aspect of the action-reaction pair, feet on wall, right? Feet on wall should be in the positive direction. So like technically what I have here is a little bit incorrect in terms of just the signs and stuff. So I'll just adjust this. So feet on wall is positive because it's pointing in the right direction. So that's positive. Wall on feet is negative, right? Force is equal to MA. So I have this MA here correct. Now, when the force from the wall is acting opposite to her, right, or pushing up against her as well to give her that propulsion forward, right? She's moving to the left as indicated into the picture, right? So if she's moving to the left, she has an acceleration of 1.1, then her acceleration is going to be a negative. Oops, let me adjust that here. Negative 1.1 meters per second squared. So I can throw in that negative sign with the acceleration here to give me an overall negative force. Because wall on feet would be in the negative x direction, right? So that would mean that, oops, let me erase that here. This should be what, negative 71.5, right? Right, this is negative 71.5 for that acceleration portion here. But then, because we know this is an action-reaction pair, right, negative of this aspect right here should give us an overall positive 71.5 newtons. So here is where the action-reaction pair stuff gets a little bit tricky because this is positive, right? We want a final positive answer. This force here is acting opposite to it, right? But in order to make them equal to each other, all our signs have to kind of match. So going back to it again, my feet on the wall is in the right direction. My feet are pushing against the wall to the right, so that's positive. The wall is pushing on my feet in the negative direction, right? At the same time, so I have this sign out here, kind of outside the parentheses. At the same time, F equals ma for the wall on feet. There's a negative acceleration associated with the fact that I'm being pushed by that wall in the negative direction, giving me an acceleration of negative 1.1, right? So if I have this wall on feet being a negative force, the negative of that negative force is going to give me the force that is equal to the feet on the wall. And in that case, negative of negative 71.5 would be equal to 71.5, and that's positive. And that makes sense because this force was directed in the positive x direction. Does that make sense? Okay. Yeah, because she's moving left, and if she's accelerating right and she's moving left, she's speeding up, she's pushing off that wall, she's swimming forward right in the left direction, it should be negative. Does that make sense to everyone else as well? Any questions about the action-reaction pair stuff for this problem? Are we all good for the action-reaction pair stuff? I mean, I just usually kind of think of it as, if this has to be positive, like I know this force for a fact is positive, and I know this force for a fact is pointing in the negative direction. Negative does not equal positive. Negative of a negative equals positive. That's how I think of it. That's why you have to throw in that negative sign outside of the parentheses in context of the problem. So, like, I know that wall on feet is pointing in the negative x direction, right? The wall pushing back on my feet. And I know that the feet on the wall is positive, right? Negative does not equal positive, right? So this is positive. I know this is pointing in the right direction. And I know that the wall on feet is pointing in the negative direction. Negative does not equal positive. I have to add another negative sign. So the opposite of a negative sign, right, is equal to the positive. Negative of a negative is positive. So that's where they come up with the whole action-reaction pair idea, right? It's equal in magnitude, just opposite directions, right? So I know for a fact this is negative. I know for a fact this is positive. They're not automatically equal to each other. But if we take the negative of a negative, that's positive, right? Or the way I had it first, the way I had things going first, where I had this negative sign here, right? You could also kind of do it that way, because negative of a positive will give you that negative. So you just kind of have to like add negative signs to either side to ensure that both sides are equal in magnitude, right? And that they have the same sign, because like this would be negative 71.5 and this would be equal to 71.5. Those are not equal to each other. So you have to do negative of negative 71.5 to get you that positive 71.5. Or if you had negative 71.5 here and 71.5 there, you can have a negative sign there, which is what I had at the beginning, if you notice. That's why I had the negative sign here. So either way it kind of works. It's just a matter of setting things equal to each other and realizing that, okay, if I have this force here, I know that this is in the negative direction. I know this is in positive, right? I want to adjust them that they're equal to each other. I can either calculate for the positive of the opposite direction or the opposite of the negative direction. Opposite of negative is positive. Opposite of positive is negative. So hopefully that makes sense for the action-reaction pair stuff again. Hopefully that little part at the end helped kind of explain things. This is another good example, problem 9 here, because it integrates the kinematics from the last couple of weeks. Let's see here. Yeah, these last couple of multiple choice questions also would just be good to kind of practice some concepts. But this one is problem 10. I would also do this one just because it gives you that sense of going over like the directions of forces and stuff and how to write the F-net equations, making sure you're plugging in the correct signs and values for all your forces. But other than that, I think that's it for the online homework on what to review. Those couple of problems I think are important. With regards to the slides, for the lecture slides, if you have issue with Newton's third law again, I can upload these lecture slides if you don't have Professor DeJong. And there's a really good example here with a baseball that kind of explains, again, the action-reaction pair stuff. I don't think this is going to be the biggest issue, the action-reaction pair stuff. I would still go over it because there could very well be a problem about it. I can definitely see that. But usually, like, if I had to guess what the quiz is on tomorrow, I'd say maybe there's a part, at least, that's talking about Newton's third law. But there's for sure going to be a lot about Newton's second law, for sure. So I would make sure that you got this first part here. So let me scroll up a bit to Newton's second law, if I can find it here. Yeah, Newton's second law. So I make sure that you understand especially this bit here, because I went really into detail about this part. The direction of your acceleration vector is the same as the direction of your net force. So if your acceleration is positive, like in that problem where we were pulling the cabinet or whatever, right? If acceleration is positive, then your net force has to be in the positive direction, has to be in the right positive x direction, for example, right? Or positive y if we're talking about y direction forces. So you have to make sure that your direction of your vector, the sign for your acceleration, is the same sign as your F-net. That's really important. Here's a conversion factor for the pounds to newtons and stuff. So 1 pound is equal to 4.45 newtons. if on the quiz, and I don't foresee this happening because they just did us dirty with that question, to be honest. Like, it was just, um, it just threw some people off. It wasn't horrible. It's just that a lot of people, I think, really try to convert things to newtons. If everything is in pounds, stick with the pounds because that's still a unit of force. But if they like throw in a couple of pounds, maybe a newton here or there, then you'd have to kind of convert to make sure everything kind of adds up. But I don't think that's ever going to happen. Um, but I mean, it's good to know, I guess. Um, let's see here. Yeah, these are just kind of quick checks again that you're understanding all the Newton's second law stuff. Free body diagrams are really important too. Figuring out how to draw them, how to make them proportional to the context of the problem. So if there's a net force in one direction or another, right, draw your vectors in a way that shows that. So if, like in that problem with the cabinet, right, if the FT, or if we figured out that the net force was to the right, so then your kinetic friction force has to be greater than your tension force, for example. So you have to draw that vector length longer than the tension force. So you have to make sure that your vectors are proportional to the context of the problem as best as you can. So they just do a couple examples here about the free body diagrams again. Yeah, just more free body diagram stuff. Figuring out how to set up F net X, F net Y equations. We went a whole bunch into that with the written homework and with the quiz and stuff. So if you still have problems with that, I would go over that as well. And then, let's see here. I don't think there's anything of note, no specific problem that I feel is like super important. Normal force, again, I went over that a million times with regards to it being the force that is always directed perpendicular to the surface of contact, right? So if we were on an incline, if they gave you an incline and the box is like this, right? Normal force would be what direction? Yeah, exactly, up and to the left. Yeah, exactly. Because if we're doing this incline, we're labeling tilted coordinates, y and x. So this is y. It would be like your slanted y or tilted y direction. So it's perpendicular to the surface of contact. The surface of contact is this incline, makes a right angle with it, upwards to the left, kind of. And that's a really important thing too. I forgot to indicate that. So whenever you have a problem with an incline like that, you can't just start drawing things and just, you know, that's it, right? They will count you off if you do not indicate that you have tilted coordinates. Like literally, if you have an incline problem, please, please, please write this to the side. You can just have like a little asterisk and put tilted coordinates and draw little tilted y and a tilted x and say this is positive y, positive x next to your drawing or somewhere on the problem to indicate that you're using tilted coordinates. I mean, it's kind of stupid because like if we have an inclined plane, I mean obviously what else are we going to use, right? It doesn't make sense for us to use the normal positive y, positive x like that. You'd have to use tilted coordinates, but it's 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 kind of stupid, but you will lose points if you don't list that you have tilted coordinates. You have to define your coordinates. So if you ever see an inclined problem on the quiz or on an exam, please, please, please put your tilted coordinates. Just literally just throw in a tilted coordinate asterisk, positive y, positive x to indicate you're using tilted coordinates. Otherwise, they will count you off. So that's another important thing too. This is a hefty problem here. I'd say maybe go over this one. I can upload this to the Google Drive as well. Worked examples. These involve a lot of the kinematic stuff, like integrating the net force with the kinematics. I'd go over that too, just to get some experience with that stuff, especially when you're integrating friction too and those types of concepts. But other than that, I don't see any other very notable concepts or problems to go over. Let me check the beginning here as well. Yeah, there's just vector addition to make sure you're good with that. So yeah, here's an example of the incline problem that I was talking about earlier. This would be your normal. You have your FGY and FGX. This would be like, I don't know, some other force pushing it upwards, for example. But yeah, and in this example, if they had friction, then if, for example, let's say we were moving upwards like that, what would the direction of the friction force be? So like, yeah, so if we're moving this way, then your friction force should be down and to the left, basically. So that negative x on that tilted coordinate. So you'd say negative x, basically. That would be the direction of your kinetic friction force. Because if we're moving upwards, it has to oppose that motion. So if we're moving across the tilted x-axis, so that's positive x, then the kinetic force is directed in the negative x direction for the tilted axis. And so if we're calculating net force, right, F net x, for example, the forces that would be acting on the x direction would be that F3, FGX, and then your FKX, for example. So if you were to set it up, you'd say like F3 minus FGX minus FKX, right? And then throw in your magnitudes and stuff, like I said earlier. So that's the tilted stuff too. Yeah, weight is FG. Weight denotes FG. So when we were talking about weight earlier in that problem, the 23 pounds or whatever it was, that means your FG is equal to 23 pounds, right? So weight is equal to the force of gravity. And object weight always points vertically downward, directly downward. So with regards to those problems here, your FG is literally just straight downwards here. Now it does make an angle here because we're using those tilted coordinates, positive y, positive x. It does make an angle here. But in that case, you'd have FGX, FGY as your components, but your gravity overall vector is directly pointing downwards always. There's spring force, there's tension force. Tension force is really easy to identify. If you have a rope, there's going to be tension. Spring force, I don't think we're getting into spring force at the moment. I think it's something that you guys are going to get into pretty soon, though, and especially on the lab, too. But, yeah, I don't know if they gave it. Yeah, I don't think they gave a definition for spring force, but spring force is equal to the spring constant times the displacement. So F equals kx, negative kx specifically too. But I don't think we've gotten to that point yet. At least I don't think. Friction, yeah, here's where we're defining friction. Friction, force that keeps an object stuck on a surface, prevents its motion relative to the surface, keeps it from slipping, right? Rolling friction, similar to kinetic, but for an object which rolls instead of sliding. So, yeah, in that case, like for the suitcase problem, you could have said rolling friction if you wanted to. That's fine. They're very similar anyway. Like I don't, for some reason, they just don't really use the notation for rolling friction too often in 131. Drag, don't even worry about drag until like what, maybe 3-4 weeks from now, maybe more, because we'll get into drag in depth later on. But yeah, I wouldn't even worry about inertial and viscous drag for the moment, or buoyancy force for that matter. There's going to be plenty of buoyancy force to go around. Lift, I don't think we did much with lift at all. Same thing with thrust. We didn't do things with thrust, so I just maybe like know the definition or something in case they throw it up on you. But I don't think we ever use those forces necessarily, at least for this point in the semester. And electricity and magnetic forces, those are going to come in 132, so it doesn't matter for those right now. Yeah, so I think that's it. I will upload the slides as well as the quiz review document, and then have everything uploaded like within an hour usually. Hopefully I can get that done within the next hour, so you guys have access to that. Definitely the documents will be up, just the videos, it might take a little time. Like usually they upload within 10 minutes, but I mean the processing takes like 30-40 minutes usually, just to kind of make sure it has the highest quality on YouTube. But YouTube is almost always up before Google Drive, and it works a lot better. So yeah, I think that's it. I'm gonna stop the recording now, and if anybody else has any other questions, feel free to ask after I hit stop. So that is the end of the quiz review session.